Hello. I think, hello, am I audible? I think my internet was gone. I had the bad connection, internet connection. Was I audible? Okay, now yes, ma'am. Okay, now I'm audible. That means I think I should share my screen once again. Am I sharing my screen now? Yeah, everything is gone again. I have to type. Okay. We were talking about kinematic. We were talking about kinematic theorem. So what was that? Internal work is equal to your external work, right? And what was your internal work? That is Wi. It is W suffix I equal to, that means W E. Sorry, suffix E. W suffix I is given for internal work. W suffix E is given for external work. Now, what is your Wi? W suffix I is given by plastic moment into your rotation. You have to know this, that your internal work is given by what? It is your plastic. Internal work is nothing of a beam or a member, is your plastic moment into the rotation. Okay, which is your plastic moment is m suffix p into what is the rotation? Rotation is given by theta. Since I'm not able to give the notation here of theta, I'm using this at the rate sign, okay, which you can understand it to be a theta. Okay, so internal work is plastic moment into rotation, which is mp into, that is the plastic moment, this one mp into your theta, the rotation. Okay, now again, what is your wi is equal to we, that is the internal work is equal to the external load. Now what is your external load, which is we? It is given by your force into deflection. Note it down, okay, these things. This might go if the internet connection goes. Okay, so that means what is your force? Force, that means force is nothing but your load. So we can note it, we can give it to be as P. We can write it to be P, which in your beams, any beams you find out, you will see the load is given to you, point loads. Okay, so your force, that is your P, that is your load into your deflection. Your deflection is given by delta. Now how should I give this delta symbol from here? Delta. Okay, this is given by what? This is given by P, that is your force, into your delta. Okay, got it? So your internal work, that means according to kinematic theorem, your plastic moment into your rotation theta is equal to your load into deflection. Okay, so we will see this how we can use this in our questions, this kinematic theorem, how we are going to understand by solving a simple question here. Now if we take a question, let us take a question here. Your question, okay, I have to This is your question. Okay, here you have a beam. This is fixed here, this is fixed here also. Okay, from both sides it is fixed. You have a point load here at the center. Sorry, so this is your point load here. Okay, this is your point load, these are your fixed, and then we have the length of this beam is how much? It is given by L. This one is given by L, capital L. Okay, and this is your P, the load. Okay, so this is your fixed. Now your question is, okay, question is at middle load, P is acting on the beam, plastic moment is given as M, oh god, wait. Okay, fine. Plastic moment is given as M suffix P. Find the collapse load. So you have to, this is your question. Okay, in your plastic analysis, we had done the shape factor. Now we are trying to find out the collapse loads using the kinematic theory, the plastic analysis. This is a method of plastic analysis. Okay, so in this simple question, now you are having what? This is a fixed beam given to you. At the center, you have a point load. You are asked to find out the collapse load. So in this case, we are going to apply this kinematic theory. Okay, so according to kinematic theory, what we have? According to kinematic theory, we know, okay. So before going there, stop. Okay. So we have this figure here. So what we have is, this is your beam. If I see, this is your beam. From here, this is your point load here at the center. So this is your center point load. I'm going to, here we will have a deflection here at the point load. So suppose this is the deflection here. Okay, this is the deflection here. So we can draw this to be okay. you have this deflection here due to this point load. You are having a deflection here delta, which is delta. Here you will have theta. Okay, let me, these are your fixed here on both the sides. It is fixed your beam. So here again you are going to have these thetas. Okay, so this is your deflection delta. This is your deflection delta. You are having a theta here. Here also you are having a theta angle. This is your theta. This is also your theta. Both sides, this is at an angle. This deflection is at an angle theta from here, and from here also to theta. Why we are taking both sides equal? Because this is L and your point load is at a distance from here L by 2 at the center. Okay, in the question, sorry, I forgot to mention here. But this is your L by 2. Sorry. This is capital L by 2. That means at the center, your this point load is at the center. So since this is at the center at a distance, equal distance from both the ends, fixed ends, so we can take this theta to be same, which is theta. Okay, and if this is theta, this angle will also be theta. Okay. So we will have this angle. This also can be theta. Here also you will have this angle. This also you can take it to be theta. So we will have these two angles will be theta plus theta is equal to 2 theta. Okay, fine. So we have this, you have the deflection here due to this point load you at an angle theta. This is your L. This is your L. So now what is your, we know according to kinematic theorem, if we apply here now the kinematic theorem, this is your deflected diagram. So we have what? This is your internal work done should be equal to the external work done, right? So for that we have to find out what is our internal work done. So what was our internal work done? You see here, that is plastic moment into rotation. Plastic moment is mp into theta. So what we have is, okay, one more thing before we go to this, we know plastic hinge, where you will have plastic hinges. Okay, where we do we have, whenever you have a fixed support, there you have plastic hinges. Okay, this plastic moment, where this will occur in the plastic hinges. And where do we have plastic hinges? We have always our plastic hinges here at the fixed supports. Okay, then under the point loads we are having, that means, okay, and also we are having at the point of zero shear in a span subjected to UDL. Whenever it is a UDL, then at the point of zero shear we will have a plastic hinge. Okay, and also you may have some beams where this geometry is different. Suddenly your geometry was a rectangle, suppose this is a rectangle, and then this goes upward, so there is a change in the geometry. It may become an I section or L section. If there is a change in geometry, so that will be there also, you will have a plastic hinge. Okay, if we want, we can write it here. Okay, so you can note it down. This plastic hinge will form where we have what? Number one, at fixed supports, under the point loads. Then we have at sections, um, where sudden change in geometry shear in a span subjected to UDL. Okay, so where do these plastic hinges form? At the fixed supports here, and then at the point loads below the under the point loads, at the sections where the geometry will change. But here what we are having. So here we will check where is our plastic hinge formed. Okay, so here if you see, your plastic hinge is formed here, this one, this is fixed here, so this has plastic hinge here. Since this is fixed here, one plastic hinge will be here, one will be here, right? Because it is your plastic hinge is formed where? Here at this fixed ends at the below the load, okay, under the load. So there are three plastic hinges. So now if we see what is our this one internal, we were talking about the internal work done. Okay, so what is the internal work done? Here we had our internal work done is how much? Plastic movement into rotation. So plastic movement, if we see now, what will be that? This will be m suffix p into, okay, let me give in bracket this thing, otherwise mp into theta, and I'll show this to be theta. At the rate, consider it to be theta, otherwise it's difficult for me to note. Okay, mp into theta, plus we are having what? This is your mp into this theta. Then we are having again here, we are having a plastic hinge. So here mp, another plastic moment mp into, now what is the theta here at the center? We are having how much theta? 2 thetas are here, so that is twice theta. So 2 into theta, plus again we are having here a plastic hinges there, so that is mp into theta again. So mp into your at the rate, that means theta. Okay, fine. There are three plastic hinges, and according to this we are having internal work, plastic moment into rotation. Plastic moment here is mp, 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 and this is theta is here theta, theta, and here it is twice theta at the center. Okay, so what we have now, the total internal work done is how much? Mp into theta, 1 mp into theta, 2 mp into theta, plus 1 mp, that means 4 mp theta, 4 mp theta. So total is how much? 4 mp theta, right? Now again, now what we have to calculate? We have to calculate the external work done. Now what is the external work done? What was your external work done? Your external work done was P into delta, that is force into deflection. Okay, now what is the force into deflection here? This was P into delta, P into, okay, delta I have to, right. external work done is P into delta, right? We are having P into delta. Now, what is your delta? You have to find out what is your delta. To find out delta, you can see this one. Here you see this angle. You can take this triangle or you can take this triangle. Consider this triangle or this triangle to find out your delta. Now, if you see these angles, suppose we are looking this triangle here, we are considering this triangle. Now, what you have, this is your L by 2. From here to here, you are having L by 2. Capital L by 2. This is your L by 2. This is your theta. So, from this triangle, we can have tan theta is equal to how much? Your tan theta will be delta by L by 2, perpendicular by base. So that will be, right? So this will be your this delta by L by 2, right? So tan theta is how much? Delta by L by 2. Where theta is your very small, so obviously this will become how much? Theta. So this will become theta is equal to your delta by L by 2. Theta is equal to your delta by L by 2. Okay, delta by L by 2. So that means what? You have your P into, what is your now external load, external work done. External work done is P into delta. P into what is the delta? Sorry. Okay. From here we can find out our delta, right? So what is our delta here? Theta into L by 2, right? So delta, from this you can find delta. Delta is equal to theta L by 2. So P into theta into L by 2, L by 2. Okay, so we have our delta is equal to theta into L by 2. So delta here I have written to be P into theta into L by 2. So now if you see, according to kinematic theorem, what we have, internal work done is equal to your external work done. So therefore what you have, your, since, okay, whatever, I have already written here, the work done is equal to internal work done is external work done. So therefore what will happen? For your MP, your 4 MP, which is your this 4 MP into delta, 4 MP into delta, this is your 4 MP into delta, this equal to this. So this will be how much? Capital P into theta into L by 2. So L divided by 2. From here, this is your equation now, which is 4 MP plastic moment into your theta is equal to the load P into theta into L by 2. Okay, we had to calculate what? Find the collapse load. So obviously we can find out this P here. Theta is gone. This theta is gone. Theta cancel. Right. So we will have here this one. So we can get our load to be How much? 8 MP divided by L. Yes or no? 4 to the 8 MP by L. Yeah. So this is your collapse load. Okay. This is your collapse load, which is your this. So understood the how to apply this kinematic theorem here, which is internal work done is equal to external work done, and you are going to calculate it here and find it the collapse load. You can calculate your collapse load. This is your plastic analysis, one kind of method of plastic analysis. So here this is your answer, 8 MP by L. Okay, plastic moment by L. Done? Clear? Take a screenshot, or if you have noted then tell me. I'll because if I go down, these annotations will get removed. Okay, it will get erased by itself. So if you want to take the screenshot, or if you want note it down, just inform me if you have done. We will do the we'll try now the second question. Done, everyone? Okay, okay, okay. Okay, sure. Okay, then if everybody is done, I'll remove these annotations here. Okay. Okay. Okay, then we'll take the next question. We'll take the next question. Here, yeah, question 2, if I show you, I'll show you exactly. I'll show you. This is your question. This is given here, a beam. This is fixed here. This is fixed here. You have a hinge here. Okay. Then we have a load here at the center. Okay. This is given by your L. This is your L. This is your fixed. Okay, I can save the notation also. Okay, the meeting is going to over now. Where is my annotation gone now? Shall we start the second class also now or at 1 only? Because now there is 5 minutes. At 1. Okay. I think you also have to go for lunch maybe, hostelers. Okay, then 1 p.m. we'll meet at 1 p.m. I'll give the attendance for this class and that class will be same. So, because that's why I'm not taking here the attendance now. Okay, so at 1 p.m. we will join. Okay. Okay, then I'll end the class here. Thank you.